Hi there, how you doing? All right. Okay, Sheridan students, today what we're going to do is we're going to talk about thermocouples. They're a little bit different than the RTD. A thermocouple isn't a resistive device. It's a device that actually generates a voltage when it's exposed to a temperature. And they have to be compared. The temperatures that it's measuring is compared from the measuring junction, is the thermocouple we're using, to a reference junction where it's connected into the instrument. Let me show you. This here is a thermocouple. This is the ones that we're using. You might be familiar with ones that come with your kit, and they come with your kit. That's actually a thermocouple. And the ones that come with your kit are K-type thermocouples. The ones we're using today are J-type thermocouples. As I actually have the thermocouple connected to my voltmeter, and what you see is it's actually reading 0 volts. Now, I did say, yeah, it's exposed to a temperature. Obviously, that there's heat in here. If there wasn't, I'd be standing like that. That would be detrimental to my health. And if you look at this controller here, what we're showing here is 21.4, 21.5 degrees. And so we're looking at this going, okay, so the 0 volts that's coming off of it. Let's look at our chart. Still in the lab, Professor Kennedy had furnished us with a lab here. And what we look at is thermocouple voltage. So I'm going to enter it in millivolts. I look here, what I've got is 0 millivolts. That's showing me 0 degrees C. So I go 0.0 millivolts, 0 degrees C. All right. And now what we're going to do is we're going to look at transmitter. The transmitter we have here, we actually have a thermocouple connected to the transmitter. Both are sitting out subjected to room temperature, just like the other ones here. What I'm reading here from my transmitter is precisely 1 volt. So I put that into my lab here, 1 volt, 1, and it's asking me for calculated temperature. So what I do is I use this formula here for calculated temperature. And that is process variable is equal to the signal minus the offset. Well, this transmitter is 0 to 5 volts. There is no offset. If it was a 4 to 20 milliamp transmitter, the offset would be 4. We go minus offset over span, and it's a 0 to 5 transmitter, so the span is 5 volts, times the range. Well, the range of our transmitter is actually 0 to 100 degrees C, a range of 100 plus the lower range value, which is 0. So if I do this calculation, which is 1 minus 0 over 5 times 100, if I do that, 1 divided by 5 times 100 gives me a value of 20 degrees C. Now, that's saying, okay, well, this is 21.5, I'm reading 0. I've got measurements all over the place. This is the actual temperature of 21.5. This here will be out a little bit because our transmitter hasn't really been properly calibrated. So what we'll do, we'll enter in our values, and at the end of the experiment, we'll be able to see what's happening here. So the calculated temperature is 20 degrees. Controller display 21.5. Okay, so now what we're going to do is measure a cold liquid, which we have here. As you can see, what we're reading here is 0 degrees C. That's on our controller. The output of our transmitter here is 0. Now, let's have a look at what our voltmeter says. Let it be aware that unfortunately I picked a voltmeter where the batteries weren't so good. They've died out on us, so what we would really read on our voltmeter is a minus 0.946 millivolts. That's what we would normally read on the voltmeter. We read that just before the batteries died. And what we're going to do is enter that into our lab here. So we're looking at thermocouple voltage, which is minus 0.946. And then we have the temperature from our chart. So what we have here is minus 9.046, which is minus 21 degrees, minus 21. Even our pen is giving out here. This pandemic's getting to everything. Okay, what we've seen is what it's measuring is a minus 21 degrees, but we know that the ice here is at 0 degrees C. Let's do the calculation from our transmitter. So if we look at our transmitter output voltage, it's 0. And calculated temperature from that, the signal is 0. Offset is 0. Our span is 5 because it's 0 to 5 volt transmitter times the range. The range of our transmitter is very simple. It's from 0 to 100 degrees C. If it happened to be, say, from minus 10 to 100 degrees C, the range would actually be 110 degrees C. But in this case, it's only 100. So we have 100 plus the lower range value of 0. So what we have is 0 divided by 5 is 0 times 100 is 0 plus 0. That comes out to 0 degrees C. 0 degrees C, controller display is 0. All right, so let's look at what we've got now as a hot liquid that we have a thermocouple put into. What we have here is the controller showing us 71 degrees, and what we have coming from our transmitter is 3.5 volts. So now if I was going to do that calculation, I would go that the transmitter output voltage is 3.5 and our calculated temperature to if we do remember the offset is 0 and low range value is 0, that ends up at 3.5 divided by 5 times 100, and we do calculated temperature is 70 degrees C. The controller display now it's actually reading 70 right now, so I'm just going to put down 70. Okay, they are correct. Now, what we might want to do is let's have another look at our voltmeter. What we're having a little bit of an issue because the temperature is dropping so rapidly. So we took another shot at taking a voltmeter reading. We got it up to the temperature, 70 degrees. And what we see here is 2.6 millivolts. So if we look at our chart, 6 I have here as right there, actually right here, sorry guys, right here, which is just a little bit above 50. And this here is going to be 50.5. Here is that we have 70 degrees. We're supposed to take D minus B. D is 70. Comes out to 19.5. It's a little off, but one of the reasons for that is the connection we have with our thermocouple. We don't have a pure J-type connection because of the type of material that we're using, but it's very, very close. 19.5. With this one here, what we have is D minus B. D minus B is 21, because remember that's a negative number, and D minus B here is D minus 0, that's 20. What we have here is 20, 21, and 19.5. Really, this is really consistent, showing it's about 20 degrees difference between each one of these measurements when we do a direct measurement of the thermocouple. And that has to do with the difference in temperature between the measuring junction and the reference junction where we have our voltmeter connected. We have to keep this in mind every time we do a direct measurement. We're not going to get an exact measurement. What we have to know is that there's going to be a difference. Our transmitter is actually giving us a correct reading. The reason for that is inside the transmitter is a circuit that gives us cold junction compensation. What it does is it allows that the cold junction, the connection here between the thermocouple and the transmitter, it actually fakes a 0 degrees C. So everything is referenced from a 0 degrees C. That's why it gives us an exact reading of the temperature. Same with any controller that we use with that. The controller has cold junction compensation.
Mr. Thermocouple, can I have a word here about your match against RTD?
Oh yeah, RTDs are nothing. They can't take the heat. I've got my two dissimilar metals. I'll put them together and I get voltage. The RTDs, there, I'll smash them because I have a bigger range. I can match any temperature. I don't have to get out of the kitchen.
Wow, that looks terrifying here. Let's check in and see what RTD has to say about his upcoming match.
RTD, what are your thoughts on your match against Thermocouple?
Give me that thing. Thermocouple, he talks about the heat that he can handle in that kitchen. Well, don't forget that it's precision over power, and I've got the best accuracy. Not to mention, I am the ultimate resistance. My God, this is going to be one heck of a match. I guess we'll find out very soon. Have a good night.